Okay. Any quick comments about the quiz? Any issues accessing the quiz or uploading your files? Questions, comments, concerns? Okay. Um, Now, what we are going to do is we are going to continue from where we left off. In the last class, we started talking about power, right? Power. And I mentioned that it does not make sense to minimize power in isolation because um, if I minimize power in isolation, the delay is going to tend to infinity or it's going to approach a really large number. So a more interesting idea or a more interesting performance metric is the power delay product or the energy. Okay, so this is a more reliable performance metric that you want to minimize so that the total energy consumption per cycle is minimized. Okay, so that way we are paying attention to both the power and delay in unison and not one at the expense of the other. Okay, that's the idea that we discussed in the last class. Also, I mentioned that the CMOS power consumption has two main components, the dynamic or the switching power or the static power. Dynamic power is what the power that is consumed when the circuit is doing useful work. Okay, it is switching the capacitances, the load capacitance from 0 to 1, 1 to 0. Okay, 0 to 1, charging the capacitance between 0, 0 to 1, and discharging. Okay, and as a matter of fact, we saw how this charge and discharge cycle happens. I'm going to talk about that a little bit more. But the total power is the dynamic power plus the static power, which is mostly leakages when no useful work is being done. Okay, leakages and contention current. We saw the general expressions, the very well-known expressions for the power in terms of the instantaneous current and the instantaneous voltage, the expression for energy, and of course the average power. Okay. Now, in addition to that, we looked at the power expression for different circuit elements. Okay, what is the amount of power supplied by a voltage source? What is the power dissipated in a resistance? Okay, and of course, what is the charge stored in a capacitance? The charge stored in the capacitance takes the form of half CV squared. And I talked about this half kx squared or half mv squared form that is very familiar. The kinetic energy stored, the kinetic energy of a moving body, or the energy stored in a spring. And we are familiar with this half times some constant times a variable squared for energy. Okay, very similar is the energy for capacitance, half CV squared, where C is the capacitance and VC is the amount, it's the voltage that the capacitance is charged to. Okay, and I mentioned that power or energy is drawn from the power supply only during the charging phase. So if you were to look at the charge followed by the discharge phase of a capacitance in CMOS logic circuits. So I'm talking about this phase where the capacitance, the load capacitance, okay, goes from 0 to 1, followed by the phase where the capacitance goes from 1 to 0 volts, okay, or logic 1 to logic 0. if you think of this as one complete cycle, okay, a total of CL VDD squared, that is the total energy drawn from the power supply. So that's the energy that is drawn from power supply, CL times VDD squared, okay? And this happens only during the charging phase when the pull-up network is active. And you have to remember, you have to notice that only half of that guy, of the total energy drawn, is stored in the capacitance here. Okay, the rest of the half CLVD squared, the rest of the energy drawn from the power supply is dissipated in the PMOS. So when the capacitance is transitioning from 0 to 1, half of the energy is dissipated in the PMOS, and then the other half is stored in the capacitance. When the capacitance transitions from 1 to 0, that is when all the energy is dumped to ground and it is dissipated in the PMOS transistor as heat. So if you look at this full cycle of purple followed by blue, only during the purple phase is energy drawn from the power supply. During the blue phase, where the capacitance goes from 1 to 0, the stored energy is dumped to ground. Okay, so this is one full cycle that characterizes completely how a CMOS uh, consumes power in the dynamic state. Okay, and then I also showed you the different waveforms, okay, and pointed to the fact that there is a teeny tiny region, okay, um, instant where both the PMOS and the NMOS are momentarily on in the saturation region, and that this can be correlated, if you remember, to the DC transfer curve, okay. The regions of operations can be correlated to DC transfer curve, okay, for an inverter. When the PMOS is in saturation, the corresponding NMOS is off. When the PMOS is in linear, the NMOS is off. When the PMOS begins to turn off, the NMOS turns on in saturation and later moves into linear region. So all of these regions of operation can be correlated all the way um, to the DC transfer characteristics that we discussed. And then we want to remember that there's a blip of tiny amount of current when both the PMOS and NMOS are on, and that's called short circuit current. Okay, we discussed this in the last class. Now, I also gave the expression for power switching. Okay, the idea for power switching is that it's a function. Okay, the switching power is a function of the capacitance times BDD squared. Okay, so we know this. That's the total power drawn from, that's the total energy drawn from the power source. And if for one cycle, and if the capacitance switches with a frequency of SW, then the power consumed will be this guy. So that's easy to see once we realize that this term represents the energy drawn, consumed for one full cycle of charging and discharging. Okay, the rest is easy, very straightforward to see. Okay, now I also mentioned, and here is a tidbit of information. The frequency of switching. If you take an example of your laptop processor, when it is plugged in, okay, it tends to operate in the gigahertz range at a higher frequency. Okay, and then it can consume larger power. Okay, uh, more power. Okay, when it is running on battery, in order to reduce the power consumption and extend the battery life, typically what is done is the processor is slowed down to operate in hundreds of megahertz range. That way, as the frequency of charging and discharging of capacitances comes down, along with it, the power supply, the power consumed also comes down, and therefore extending the battery life. So one mechanism to extend the battery life and reduce the amount of power consumption is to lower the frequency, but a bigger knob to control the power supply, the power consumption, is to reduce the supply voltage, power supply, because it has quadratic effect on the power consumed. Okay, so that's one of the things that we discussed in the last class. And so far it's only power switching. Now, if we want to express, now if I want to express the power supply in terms of the master clock, what can be done is frequency of switching can be expressed in terms of the activity factor times F clock. Once we take that into account, it's easy to express the power switching as a function of uh, activity factor alpha, capacitance, CVDD square, and this. So alpha times F clock, that replaces FSW, okay? So I'm expressing the power switching in terms of the master clock. That's all I'm doing here, okay? This is what we looked at in the last class, okay? And then I mentioned that the short circuit current, the teeny tiny blip of current, is actually a very small percentage, 10% of the total dynamic power consumed by the CMOS circuits. Okay, so that is what we discussed. And I also mentioned that the total power consumption is equals to the dynamic power consumption, which is doing useful work, plus the static power consumption, which is mostly the static power consumption is mostly leakage currents and contention current. Okay, we look at contention current when we look at ratioed logic. Okay, and then this contention current is not present in CMOS. In CMOS logic, it's only present in ratioed pseudo NMOS, or that kind of logic where both PMOS and NMOS are simultaneously on. Okay, so the dynamic power itself is the sum of the switching power and the short circuit power. Okay, this is something we discussed in the last class. And then we came as far as this, looking at an example problem, and that is where I want to take up, that is where I want to begin now. So any questions so far, please?
Dr. Vittori, the contention power is regards to pass gates?
It's regards to pseudo and MOS logic. The contention current, right?
Right.
So that's a good question. The idea is in PMOS transistors, in CMOS logic gates, okay, the input is driving both the gates of the NMOS and PMOS. So when the NMOS is on, PMOS is off. When the PMOS is off, the corresponding NMOS is on. So this is the idea in CMOS logic. Okay, what if I don't implement an inverter using a CMOS logic, but I implement an inverter using a resistance and one NMOS transistor? Okay, it is possible to do that. What if I implement the CMOS logic using what is known as a pseudo NMOS transistor? Okay, so this, I'll show you an example. So this guy is a pseudo NMOS implementation of a two-input NOR gate. Okay, in this two-input NOR gate, the pull-up network has one PMOS transistor that is always on. Okay, that is always on. So when you want to turn the pull-down network on, you first have to overcome the effect of this PMOS transistor and then discharge all the capacitances to ground. So the idea is contention current is relevant in situations where both the PMOS and NMOS are on simultaneously. Okay, and so the NMOS transistor has to contend with the PMOS in charging. So this is pseudo NMOS logic. So to answer your question, we will look at this kind of transistor circuits where both PMOS and NMOS are on simultaneously. And that is where one has to fight the other. The NMOS transistors have to contend with the PMOS transistor when discharging a capacitance. And that is where the contention current comes into picture. Okay, so in CMOS logic, contention current does not come into picture. Okay, does that answer your question at all, Vivian?
Yes, it does. Thank you very much, because I was testing the NAND in the north that I have, and I was keeping one input always, for example, for NAND, always on. And then it was the one that was close to the output. And I noticed that I was burning a lot of power. It was almost double.
Yeah. That's mostly because of the contention current, because these NMOS transistors here have to contend or counter act the effect of the PMOS and then overcome. So the bottom line is we don't have to worry about that problem in CMOS logic. Okay, when one transistor is on, the complementary transistor is off, and vice versa. That becomes a problem in other ratioed logics. Okay, we'll talk about that shortly. But now, so let's look at the problem here. Okay, so what I'm going to do is I'm going to write out the given terms here and then try to solve the problem for there. Okay, so let's try to write what is given in the problem. Okay, it is important that we read the problem carefully and interpret it accurately. Okay, what is given is VDD, that's given to be 1 volt. Okay, and it's a 65 nanometer process. Okay, and then lambda, this is a term that we are not familiar with so far, is given to be 25 nanometers. Let me talk about lambda here. It's a very popular scaling parameter. Okay, for layout purposes. It's useful for layout design rules, also called as lambda-based rules. Okay, lambda-based rules. What it is a scalable parameter that characterizes the process technology. Okay, if it's a 65 nanometer process, for that particular process, lambda is given to be 25. Then what we can do is the lengths, widths, and all the spacing parameters can be expressed in terms of lambda. Okay, so it's a single parameter that can be used in a bunch of different places to characterize the lengths, widths, spacing, so on and so forth. And it can help when we are translating from one process technology to another. And the GM, GDS values, other process parameters will also scale based on this. So the idea is it's a constant. I will give the value of that constant for each particular technology. If it's a different technology, I will give the corresponding lambda for that in the problems. Okay, so lambda, and then typically length minimum happens to be 2 times lambda. Okay, this is, or the minimum feature size possible is typically a function of 2 times of lambda. Okay, so that is given, lambda is given, and I will show you how we can use it in the problem. Okay,
Dr.
so that is,
Midri, sorry, I have another question.
yeah.
How we can know the lambda value if, for example, you have 90 nanometers process and you needed to convert it into 800?
Yeah, it's usually given, and then we rely on given information to arrive at that lambda.
Somebody needs
Okay,
to give that
so in
information.
this
Okay.
case, yes. So in this case, the lambda is given to be 25. And then what is also mentioned is the number of logic gates, the number of logic transistors is given to be 50 million. Okay, 15 to 10 to the 6th. The number of memory transistors is given to be 950 million. Okay, so that is given. And then what is also given is, let's see, the average width. Okay, the average width of the logic transistors is 12 lambda per transistor. Okay, and also given is the average width of the memory transistors, which is given to be 4 times lambda. So it's easy to see how we express all the widths, lengths, and all the sizes in terms of lambda. Okay, so that's the idea. Everything is expressed in terms of lambda. What is also given is that the switching factor of memory is given to be 0.02, and the alpha, the switching factor of the activity factor of the logic gates is given to be 0.1. Okay, it's intuitive to understand why that is the case. If you think of a hexadecimal number, so this is a 64-bit binary number expressed in its hexadecimal format. Okay, let's say this number is used to represent your bank account balance. Okay, let's say this number is used to represent your bank balance. And the data is all stored in memory, right? And it is logical to understand that the upper 16 bits of the memory, okay, upper 16 bits of the memory are, and this is all 32 bits wide. This is 1, 2, 3, 4, 8, 4, 32. So 32 bits wide. So the upper 16 bits of the memory do not change frequently. If you're using this variable to represent your bank balance, because on a day-to-day basis, not many people do transactions that are so large as to change the upper 16 bits of the hexadecimal representation of your bank balance, unless you're investing in Bitcoin, where you would end up losing a lot of your money in a single day. But if you're not doing that, if you're smarter than doing that, your bank balance usually has a lesser probability of switching. Okay, so the activity factor or the switching frequency of your memory is smaller compared to that of logic gates, which switch more often, okay, more frequently. That's the idea. Now, what else is given is C gate per width, per unit width is given to be 1 femtofarad per micrometer. Okay, that's given as the C gate. C diffusion, which represents C source plus C drain per unit width. that is given to be 0.8 femtofarads per micrometer. Okay, and then the frequency of the clock is given to be 1 gigahertz. And the question is, find out the total power consumption. Okay, so now what we are going to do is we are going to use the equation power switching, or the dynamic power consumption is alpha times C times VDD squared times F clock. Okay, so we know this is given to be 1 gigahertz. Okay, and we also know that this value, this VDD value, is given to be 1. Okay, the alpha values are given, and more information is given for us so that we can arrive at the value for C. C is not given directly, but it is given in terms of some other parameters. So let's see how we can calculate C first. Let's calculate the C of the logic components. For the logic components, what is given is the CG and C, so capacitance in the gate and capacitance in the diffusion regions, okay, as a unit of width, femtofarad per micrometer is given. Okay, capacitance per micrometer is given. If I multiply that by the width of the transistor, which is given to be 12 lambda, okay, so what is given is C by W. If I multiply that by the average width, these cancel out, and I will be left with a single term that represents capacitance. Okay, so pay attention to the fact that what is given is a term that represents capacitance per length. In order to arrive at capacitance, I simply have to multiply that by the units of length. So which I am doing here by multiplying it with the width. Okay, so this is not enough. This is for one gate. I have to remember that there are 50 million of those gates. Okay, 50 million of those gates. So if I look at the C logic, the capacitance in the logic part of the circuit, it comes out to 27 nanofarad. Okay, let's calculate C in the memory, the capacitance coming from the memory. Okay, it is given to be the capacitances are given to be 0.8 and 1 femtofarad per micrometer. Okay, and then when I multiply that by the average width, 4 lambda of the memory transistor, I will get the capacitance for one transistor. And now if I multiply that by 950 million, okay, I'll get the total capacitance coming from the memory here. Okay, so lambda value, we know the value of lambda is given to be 25 nanometers. Okay, so we plug in all the values, we end up with the memory values capacitance to be around 171 nanofarads. Now we can move to calculation of power switching. Power switching is alpha C VDD squared times F clock. So let's plug this in. Alpha for memory is given to be 0.02, and the capacitance for memory is 171 nanofarads. Okay, plus 0.1 is the alpha for logic times 27 nanofarads is the capacitance for logic components. 1 squared is the VDD squared, and 10 to the 9, that's the frequency F clock. So this is alpha times C, this is VDD squared. So if I plug the numbers in, I get a value of power switching equals to 6.1 watts. Okay, 6.1 watts. And when I did the math, the individual components were around 2.7 watts and 2.4 watts. Okay, so the idea was a large capacitance coming from the memory, switching at a less frequency contributes almost the same power consumption. It consumes almost the same amount of power as a small amount of logic circuits, switching very often, consuming that amount of power. Okay, both of these components, both of these power components are comparable, and that alludes to the fact that switching factor, okay, the activity factor alpha is an important parameter. Okay, questions, please. Questions so far? Okay. So all I have done is to calculate the value of P switching using the F clock, alpha C, and VDD square. The only calculation involved was in arriving at C from the different pieces of information. Okay, for dynamic power reduction, we try to minimize the activity factor um, or the total load capacitance or the capacitance. So we are only so far looking at the capacitance in the load, CL, right? As it turns out, the wiring between different nodes also contributes quite a bit of capacitance, okay? And that can be reduced by choosing the float plan, by wise float planning. Okay, and then there is a quadratic dependence of power switching on the power supply. So that's a big motivation to operate at lower voltages. And of course, the clock frequency, as I mentioned, a laptop that is plugged in can afford to run at higher frequency because it can consume higher power. It's not operating off of battery. But if it is running on battery, it would be wise to operate at a low frequency and um, consume less power. Okay, so that's the idea. We will come back and talk about some of the problems that we did not discuss yet in terms of how to estimate the activity factor for different gates. Okay, if there is an AND gate, if there is a circuit that looks like so, okay, a bunch of a 4-input NAND gate, okay, what is the effective activity factor? What is the probability of switching? So all of that good stuff we will come back and discuss. Remember, there is no class next week. There might still be the midterm, okay? I'm waiting for directive from the dean's office in terms of what to do about the midterm. So hang tight, hang in there. We are going to, I will inform you over Canvas about the next week's midterm exam, but pretty sure there is no class next week. So the time I will see you is the week after next. Okay. Questions? Any questions before we um, disperse? Okay.